NENOMATICA, where mathematics meets YouTube excellence. Welcome to this math tutorial, where we'll learn about factoring perfect square trinomials. This is a powerful factoring technique that you'll use throughout algebra and beyond. Let's start by understanding what a perfect square trinomial is. A perfect square trinomial follows this pattern: a squared minus 2ab plus b squared, which equals a minus b squared. In other words, if you have a trinomial that can be arranged in this form, it can be factored as a binomial squared. Let's look at our first example. We want to factor y squared minus 6, y plus 9. Step 1. Express this as a perfect square trinomial. We'll use the perfect square trinomial identity. A squared minus 2ab plus b squared equals a minus b squared. Let's identify the parts in our trinomial. We have y squared, which means that it equals y. We also have negative 6y, which would be negative 2ab. So negative 2 times y times b equals negative 6y. This means b equals 3. Finally, we have plus 9, which would be b squared. And indeed, 3 squared equals 9. So our trinomial fits the pattern perfectly. Quick challenge. Can you identify a and b in our expression? Take a moment to think about it. Step 2. Now that we've recognized the pattern, let's collapse this into a square. Using our perfect square identity, we can replace the expression with a minus b squared. So our expression becomes y minus 3 squared. Step 3. Let's factor fully by writing this squared term as a product. Remember that a minus b squared equals a minus b times a minus b. So y minus 3 squared equals y minus 3 times y minus 3. Quick recap. We've shown that y squared minus 6, y plus 9 equals y minus 3 times y minus 3. This is our final factored form. Let's look at another example. We want to factor x squared 3. This is our final factored form. Let's look at another example. We want to factor x squared minus 20x plus 100. Step 1. Let's express this as a perfect square trinomial, using our perfect square trinomial identity again. In this case, we have x squared, which means it equals x. We have negative 20x, which would be negative 2ab. So negative 2 times x times b equals negative 20x, which means b equals 10. And we have plus 100, which would be b squared. And 10 squared equals 100, confirming our pattern. Quick challenge. What are a and b in this expression? Pause and reflect on your answer. Step 2. Now let's collapse this into a square. Using our identity, we get x minus 10 squared. Step 3. Let's factor fully. Using the rule that a square equals the value times itself, we get x minus 10 times x minus 10. Quick recap. We have x squared minus 20x plus 100 equals x minus 10 times x minus 10. And that's our factored form. Let's summarize what we've learned about factoring perfect square trinomials. We have the expression x plus y squared minus 4xy. This is a form that might look complicated at first, but we can simplify it by recognizing a pattern. For our first step, we need to expand x plus y squared. Using the binomial expansion formula, we know that x plus y squared equals x squared plus 2x, y plus y squared. Now let's combine like terms. We have 2xy from the expansion and minus 4xy. So we have 2xy minus 4xy, which equals negative 2xy. Looking at our expression, we now have x squared minus 2x, y plus y squared. This is a special pattern known as the perfect square trinomial, where we have a squared minus 2ab plus b squared, which equals a minus b squared. Let's move on to our second example. We have x squared y squared minus 8x y plus 16. This might look more complicated, but we can use a similar pattern to factor it. For this expression, let's look for a pattern. We'll see if it matches the form xy squared minus 2 times xy times some number plus that number squared. Looking at our last term, 16, we need to find a number whose square is 16. That number is 4. So we're checking if our expression matches xy squared minus 2 times xy times 4 plus 4 squared. Since our expression matches the perfect square trinomial pattern, we can now write it as xy minus 4 squared. As a final step, we can also write this as xy minus 4 times xy minus 4. Let's look at our third example, x to the fourth power minus 2x squared yz plus y squared z squared. This expression follows a similar pattern to our previous examples. Let's analyze this expression. The first term is x to the fourth, which we can rewrite as x squared squared. Let's see if this fits our perfect square trinomial pattern. Looking at our expression, if we let it equal x squared and b equal yz, then we have a squared minus 2 times a times b plus b squared. This fits our perfect square trinomial pattern. Now we can apply our perfect square trinomial pattern. The expression becomes a minus b squared, which is x squared minus yz squared. And we can also write this as x squared minus yz times x squared minus yz. Let's summarize the patterns we've learned in this lesson. For a perfect square trinomial, we have a squared plus or minus 2ab plus b squared, which equals a plus or minus b squared. Recognizing these patterns can help you factor complex expressions more easily. Thank you for watching this lesson on factoring patterns. Practice recognizing these patterns in various expressions to become more proficient at factoring. We have 9x squared minus 6x plus 1. To determine if this is a perfect square trinomial, we need to check if it follows one of our patterns. Let's see if we can identify the values of a and b. In our expression, 9x squared minus 6x plus 1, the first term is 9x squared. If we're looking for a squared, then a must be 3x. The last term is 1, which would be b squared, so b must be 1. Now, let's check the middle term. If this is a perfect square trinomial following the pattern a squared minus 2ab plus b squared, then the middle term should be minus 2 times a times b. That's minus 2 times 3x times 1, which gives us minus 6x. This matches our middle term exactly, so this is indeed a perfect square trinomial. Now that we've identified this as a perfect square trinomial, let's write it in its factored form. If it equals 3x and b equals 1, then using our pattern a squared minus 2ab plus b squared equals a minus b squared, we can rewrite our expression as 3x minus 1 all squared. Let's verify our answer by expanding 3x minus 1 squared to make sure it equals our original expression. 3x minus 1 squared equals 3x squared minus 2 times 3x times 1 plus 1 squared, which gives us 9x squared minus 6x plus 1. This confirms our factorization is correct. Let's move on to our second example. We have x to the fourth minus 2x squared plus 1. For this example, let's again check if it follows the pattern of a perfect square trinomial. This time, we notice that the expression has the form a squared minus 2ab plus b squared, where the variables have different exponents. Let's identify a and b in this expression. The first term is x to the fourth. If this is a squared, then a must be x squared. The last term is 1, which would be b squared, so b must be 1. Now, let's check the middle term. If this follows the pattern, the middle term should be minus 2 times a times b, which is minus 2 times x squared times 1, giving us minus 2x squared. This matches our middle term, confirming that this is a perfect square trinomial. Now we can write this expression as a perfect square. If it equals x squared and b equals 1, then using our pattern, we can rewrite x to the fourth minus 2x squared plus 1 as x squared minus 1, all squared. We can actually factor this expression even further. The term x squared minus 1 can itself be factored as a difference of squares. We know that x squared minus 1 equals x plus 1 times x minus 1. Therefore, x to the fourth minus 2x squared plus 1 equals x squared minus 1, all squared, which equals x plus 1 times x minus 1, all squared, which we can also write as x plus 1 squared times x minus 1 squared. Let's look at our third example. We have 20x squared minus 100x plus 125. For our third example, let's first look for any common factors. We notice that 5 is a common factor of 20, negative 100, and 125. So we can factor out 5 from the expression to get 5 times 4x squared minus 20x plus 25. Now let's focus on the expression inside the parentheses, 4x squared minus 20x plus 25. Let's check if this is a perfect square trinomial. Let's identify a and b in this expression. The first term is 4x squared. If this is a squared, then a must be 2x. The last term is 25, which would be b squared. So b must be 5. Now, let's check the middle term. If this follows the pattern, the middle term should be minus 2 times a times b, which is minus 2 times 2x times 5, giving us minus 20x. This matches our middle term, confirming that this is a perfect square trinomial. Now, we can write the expression inside the parentheses as a perfect square. If it equals 2x and b equals 5, then 4x squared minus 20x plus 25 equals 2x minus 5, all squared. Therefore, our original expression 20x squared minus 100x plus 125 equals 5 times 2x minus 5, all squared, which we can simplify as 5 times 2x minus 5, all squared. We have the expression a minus b squared plus 2 times b minus a plus 1. First, let's rewrite our expression. We'll start by looking at that middle term, 2 times b minus a. Notice that b minus a is the negative of a minus b. So 2 times b minus a is equal to negative 2 times a minus b. Now, let's notice what we have. We have a minus b squared, minus 2 times a minus b, plus 1. This is starting to look like a pattern we should recognize. This matches the perfect square pattern, where we have x squared minus 2x, y plus y squared, which equals x minus y squared. In our case, x is a minus b and y is 1. Simplifying inside the brackets, we get a minus b minus 1 squared. Finally, we can expand this expression to verify our answer. Now, let's move on to our second example. We have the expression a to the 8th power minus 32, a to the 4th power plus 232, a to the 4th power plus 256. For this problem, we need to recognize another pattern. First, let's rewrite the expression to make the pattern clearer. We can write a to the 8th as a to the 4th squared. Now, let's use the perfect square pattern. If we look at the number 256, we can write it as 16 squared. Now we can recognize the perfect square pattern. We have a to the 4th squared, minus 2 times a to the 4th times 16 plus 16 squared. Applying the perfect square pattern, where x is a to the 4th and y is 16, we get a to the 4th minus 16 squared. We can further factor a to the 4th minus 16. Let's use the difference of squares formula. We can factor a squared minus 4 further, using the difference of squares again. Simplifying our answer, we get the final factorization as shown. Let's summarize what we've learned about working with algebraic expressions and perfect square patterns. We have the expression 25a squared minus 30, ab plus 9b squared. To recognize if this is a perfect square trinomial, we need to check if it follows the pattern a squared plus or minus 2a plus b squared, which equals a plus or minus b squared. Let's break down our expression to see if it matches this pattern. First, let's identify the coefficients in our expression. We have 25a squared, which suggests that the first term in our binomial is 5a. Then we have 9b squared, which suggests that the second term in our binomial is 3b. Now, if this is truly a perfect square trinomial of the form 5a minus 3b squared, the middle term should be negative 2 times 5a times 3b, which is negative 30ab. And indeed, our middle term is negative 30ab, which confirms this is a perfect square trinomial. Therefore, we can factor this expression as 5a minus 3b squared. Let's verify this by expanding 5a minus 3b squared. We get 5a minus 3b times 5a minus 3b, which equals 25a squared minus 15, ab minus 15, ab plus 9b squared, which simplifies to 25a squared minus 30, ab plus 9b squared. This matches our original expression, confirming our factorization is correct. Now, let's move on to our second example. We have the expression 2x minus x squared minus 1. First, let's rearrange this expression to standard form with the highest power of x first. We get negative x squared plus 2x minus 1. Now, let's factor out a negative 1 from the entire expression. This gives us negative times x squared minus 2x plus 1. Now, let's examine what we have inside the parentheses x squared minus 2x plus 1. This matches our perfect square trinomial pattern a squared minus 2ab plus b squared, whereas x and b is 1. So we can rewrite this as negative times x minus 1 squared. Therefore, our original expression 2x minus x squared minus 1 can be factored as negative times x minus 1 squared or negative x minus 1 squared. Let's verify this by expanding negative x minus 1 squared. We get negative times x squared minus 2x plus 1, which equals negative x squared plus 2x minus 1. And if we rearrange this to match our original form, we get 2x minus x squared minus 1, which confirms our factorization is correct. To summarize what we've learned about factoring perfect square trinomials, first, identify if the expression matches the pattern of squared plus or minus 2ab plus b squared. If it does, then it can be factored as a plus or minus b squared. Sometimes you may need to rearrange terms or factor out a coefficient first. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.